Welcome back. This is video 5 of Module 6. This is the last video of Module 6. So congratulations if you've made it this far without peeking ahead. We've covered a lot of stuff, and in a minute I'll try to recap some of the stuff that we have covered so far. But first I'm going to talk about last time. Talked about a couple of data sets you can get for free from the government. The Tiger data set comes from the Census Bureau. It involves a bunch of geometries that nest within each other that are used to aggregate counts of humans during the census, but it also involves other types of geometries or geographies that you can download, and one of those is a transportation network. So you can use the Tiger data set to do what's called geocoding, and geocoding is the process of assigning a location, an X and a Y, to an address. So you give a geocoding algorithm an address, it goes out into the network that you're using, and it finds where that address lies on the network, and it creates a point feature at that point. NHD is National Hydrology Data Set that comes from the USGS. It involves surface water features. The USGS also produces geographies that involve watershed areas, and those are called hydrologic units, and the hydrologic units have codes. The largest hydrologic unit, the largest watershed, has a 2-digit code, and the smallest watershed has a 12-digit code, and these two nest within each other. So you can summarize things by watershed or watershed size also. But knowing that there's a flow data set, a network data set evolved within HD, will allow you to do a network analysis of surface water features, just like you can do a network analysis of transportation features. So those are free, available from the government. Okay, we covered a lot of stuff. We're about midway through the semester, and so it probably pays to take a little breath and go back and think about what we've covered in the first half. Way back in Module 1, I did a little introduction to GIS. I talked about what is a system, what's an information system, what are the components of an information system, and what is it about an information system that makes it a geographic information system. And remember that first law of Robichon, which is if it makes a difference where, geography matters. So if your information system involves where, it's a geographic information system. Okay. Also talked about modeling, which is a way to represent reality. You simplify or generalize some part of reality using a model. The GIS models that are used in general are the vector model and the raster model. Chapter 2 is about georeferencing. That's about modeling the where of things on a planet, on our planet or on some other planet, okay? And when you want to represent the three-dimensional smooth surface of some type of planet or our planet, you use what's called an ellipsoid. When you want to also model elevation on that surface, you use what's called a geoid, which is modeling gravity and allows you to estimate the height above, in this case, means sea level. Okay, so with an ellipsoid and a geoid, you can get a 3D model of the Earth. But you're going to need to make this 3D model into a 2D model in order to give someone a flat map. And you do that using map projections. And map projections use algorithms to project the three-dimensional location data onto a flat surface using a developable surface. And there are three types. There are planes, there are cones, and there are cylinders. Depending upon which one of those developable surfaces you pick, the projection process is going to distort your two-dimensional map in one way or another. And I talked about 4 types of distortion. Different surfaces, different projection methods give you different types of distortion. So when you look at a map, you're seeing a distorted representation of the Earth. And when you look at a map and look at a map scale, remember map scale is that ratio of units on the map to units on the real world, map scale not being the same as geographic scale. When you look at that map scale is only going to be true at those locations where your developable surface intersects with the three-dimensional surface that you're projecting from. Everywhere else, that scale isn't going to apply because you have distortion. Chapter 3 or Module 3 is about cartography, and that's about a communication model where you as the map maker are communicating a geographic message to the map reader. In order to communicate that message, you've got to use a language that the reader can understand. That language is a cartographic language, And so there are elements of that cartographic language that allow you to send a clear message to the map reader. You need to think about things like symbology. How do I symbolize things? What colors do I use? How do I classify the data? How do I break it into components? What type of map elements, additional elements, do I want to include in my map so that people can understand which way is north, or what the scale of the map is, or where the data came from, or things like that. So by using cartographic language, you're going to be able to send a clear message to your map reader, so they'll be able to understand the message that it is that you're trying to send them. Module 4 was about metadata standards, error and data quality. Metadata, who, what, when, where, why, and how. That's where your data have been before they get to you. So it's a good idea to know where your data have been, because once the data goes into your system, it's not going to get any better than the quality of the data that went in. So metadata tells you where your data's been, how good it is in those 5 W's and an H dimensions. Standards are accepted methods of gathering, processing, storing, and communicating that data. So if your data follows a standard, you're going to be able to share it with others, and they'll be able to understand the quality of that data because it follows a standard. Likewise, other people will be able to share it with you. Data quality has to do with how close your model representation numbers come out to the real world numbers, and so it's kind of about errors. The type of error that your data might have depends upon the type of data that you have. And so there are 4 types of data: nominal, ordinal, interval, and ratio. Nominal and ordinal, you can't assign numbers to those, and so those are maybe considered qualitative data. Interval and ratio data you can assign numbers to, so those are numeric data. Depending upon whether your data is qualitative or quantitative, numeric or qualitative, you'll use different methods for estimating the error. Okay, for qualitative data, you're probably going to use an error matrix to estimate the error. For quantitative data, you're going to use a more quantitative measure like root mean square to estimate your error. When you think of error, you need to think about the difference between precision, accuracy, and trueness, and so those are important concepts to keep in mind for that part of things. Module 5 got into some depth on the vector GIS model. Remember, the vector model is points, lines, and polygons. Points are locations in space designated by coordinates of one form or another. Lines are connected points. If a line has many points on it, the end points of the point of the line are considered nodes, and the interior points are called vertices. Polygon, or an area, is a line, of course, which is made up of many points, that's connected to itself. So it has closure, which means the very first point in your polygon is at exactly the same location as the very last point in your polygon. Those are the 3 types of features. Okay, that's all about the where, but all of these features also have what information associated with them. And so you need to know more than just the where, but the what that's associated with it. And in order to do that, you need to link the where to the what. And you can link the where to the what using one of 2 methods. One would be called a join, and the other would be called a relate. And those are concepts that are associated with a georelational model, in which things can be related to each other in terms of how many of one thing are related to how many of another thing. So remember, there are 4 types of relationships: one-to-one, one-to-many, many-to-one, and many-to-many. Depending upon what type of relationship you have between your spatial and your what data, you'll use a different method, join or relate, to link those 2 together. Once you've linked them together, you can select things, a subset of your data set, or you can query things, which also will give you a subset of your data set. And you can select by the whats. You can ask questions about the what and have it give you a subset based upon the what that you specify. Or you can ask questions about the why. You can say things like, what is inside of this? What is to the left of this? What is further than this from this? What touches this? Things like that, spatial relationships. So you can query or select subsets of your data using a query language for attributes, or a spatial relationship question if you want to do a spatial selection. Okay, once you can query things, ask questions of your data, and get subsets of your data, then you start deciding, what about relationships between data sets, spatial relationships between data sets. In order to do that type of analysis, in most cases you're going to use vector overlay, which involves overlaying one or more data sets with another data set. And what you'll get out of an overlay is new geography, new geometries. When you do a query, you're getting a subset of existing geometries. When you're doing an overlay, you'll get new geometries. So you can think of things like intersection and union, erase, symmetric difference, identity. There's a whole bunch of overlay tools that you can apply to overlay one data set on another data set. Okay, so using combinations of queries and overlays, you can chain those together into what's called a workflow, or a geoprocessing workflow. And a geoprocessing workflow can be used to conduct a vector analysis. And so a vector analysis is basically asking a question about your data and developing an answer using a sequence of operations that involve queries and overlays and buffers and clips and things like that, so that you can answer a question about geographic data and provide information to the person who you're going to give the map to in terms of that map language and the message you're trying to send. So that's what the vector analysis is. This is the module oriented now, the network model. And the network model, remember, involves topologically correct relationships between points and lines in most cases. And so points are connected to lines in a network model, and in a network you're going to be able to calculate a path between one point and another that follows along the network, as opposed to just going out in straight lines from one point to another. So you can imagine going from point A to point B on the roads, or from point A to point B in a helicopter, and you're going to go in different ways if you have to stay on the road, stay on the network, than if you can just fly right across from your helicopter. Okay, so there are different types of networks. There's directed networks, which are kind of like utility networks or stream networks. There's undirected networks, and the most common one of those is a transportation network. So that's what this module has been about. Okay, so that's 6 modules halfway through the semester. A lot of stuff to remember. A lot of it's important, but remember that the concepts are more important than the details, because the GIS and the hardware and software and a lot of those things that are involved in doing analyses will change from year to year, but the concepts involved will stay the same. So make sure you keep your eye on the concepts when you're thinking about what's going to be on the midterm. Next time, after the midterm, we're going to go back and look at another model that I just briefly touched on in Module 1, and that's the raster model. And so we'll spend a few weeks talking about the raster model and things you can do with the raster model. Remember, the vector model is good for discrete things, and the raster model is better for continuous things. After we go through a few weeks of the raster model, then we'll kind of wrap the course up with a few weeks with things that you can use with both the raster model or the vector model, or maybe a combination of those two. So that'll be an exciting second and a half. Good luck on the midterm, and I'll see you again after that, Module 7.